Hi, I am the theoretical Richard, so I hope to do this faster because it's a lot of theoretic part. So to start, the principle of continuity is allowed in the field of mechanic physics that explain the behavior of fluids. It establishes that what flows into a given volume at a given time minus what leaves the volume at that time must accumulate in that volume. So we have this formula to calculate the flow rate, but usually we have more formulas extended, but this is the most common. And for example, once the flow remains constant and the water velocity increase through a decrease in acromeny, as occurs in a sewer, the flow area must decrease. So we use this part to how do you say in Spanish? How do you say in English? To watch the movements of the fluid inside the across a space. In a very small space. So next is the atmospheric pressure. Um, Actually, atmospheric pressure is expressed in several different systems of units, including millimeters, pounds per square inch, dynes per square centimeter, um, millibars, standard atmospheric pressure, or kilopascals. So, atmospheric pressure is also known as barometric pressure after the barometer, and it's the pressure within the atmosphere of Earth. So, an image or an example are like this. We use the atmospheric for everything, like the lower pressure and the higher pressure, and we feel this pressure in the body or in things and or more things. And the volume the volume flow. And physics and engineering, ingeniería. I don't know how to spell it, sorry. Especially fluid mechanics, volumetric flow rate, also called volumetric flow rate or volumetric velocity, is the volume of fluid flowing per unit time, mostly represented by the letter Q, sometimes V. This is a constant to bulk flow, the other major mode of liquid flow. And we use a lot of formulas for this, the volume flow, because there will be like occasions like we have a lot of volume flow or we don't have like the data necessary to use the common formula. So we have these equations. So we use this because it's the volume of a fluid passing across sectional area per time. In this case, we can calculating the volume of fluid like in these bottles or in a container. And the Bernoulli theorem is a little bit complicated because it's the total energy per time unit mass of flowing fluid at any point in the surface. It's like the total energy accumulated in the container or in a surface. In this case, in the experiment, was the water inside the bottle. So the Bernoulli theorem is a principle like about how the velocity of a fluid relates to its pressure. In this case, one example where like the the speed of a water while we open the bottle and while we close again the bottle was different. So we use this Bernoulli theorem in this. And finally, to not extend this too much, Torricelli theorems. So Torricelli's theorem is similar like Bernoulli's theorem. So But in this case, it's like the gravity and how this affects the speed of a water. In this case, in the last part that I mentioned was like close the bottle and open, but in this case, we take the bottle and we change the position, and obviously the gravity affects the speed of the water. So finally, the Torricelli's theorem is the velocity of a liquid flowing through an orifice in a tank under the force of gravity. With flowing through an orifice in a tank under the force of gravity, and it's proportional to the square root of a vertical distance. So, the Bernoulli's equation can be considered as a statement about the appropriate beginning of energy conservation for moving fluids. And I mentioned the Bernoulli equation because it's something related to the Torricelli's theorem. So, actually, we have really similar formulas. I mean, we have like this formula, and it's similar to the other formulas of the Bernoulli theorem. So, it's actually Torricelli is like the gravity, and Bernoulli is the speed of a surface. And this was all the theorem, I mean, all the theoretical part, because was really, really, really extent.
Hello, my name is Mariana Lores Bustamante and I was the experiment maker for this practice. In this practice, I learned a lot about fluid dynamics and how the atmospheric pressure can affect how the flow of the liquid started and ended. When I would unscrew the cap of the bottle, the liquid would pass through really quick, and then after tying the cap, then the liquid would happen like some seconds until it stopped, the flow would stop. So with this experiment, I learned a lot how with the pressure of the atmosphere and also the pressure that the cap was exerting on top of the water would stop or allow the liquid to flow. And also it was really interesting getting to do this thing because sometimes we do other practices with other things. Thank you.
Hi, my name is Mariana Gonzalez Torre, and what I conclude about this experiment is that, as we can see, after a few seconds of closing the bottle, the water stops flowing through the hole. This is because when the bottle is kept closed, the internal pressure on the hole is the same as the external pressure outside the bottle. However, the previous equilibrium is broken when we open the bottle again, allowing the air to enter, changing the pressure, and breaking the superficial tension in the hole. The difference of this pressure causes the water to leak from the bottle, causing the experiment that we have made. Thank you.
Hi, my name is Alejandro Garcia Medellin. I'm the team coordinator. And first of all, after doing this experiment, I found very interesting that when you close the bottle, it won't stop the dripping of the water on the bottom because of the pressure that the tap applies. And also, after this practice, I learned to apply the Bernoulli's theorem and the formula, as well as the Torricelli's theorem and its formula. And I learned about the principle of continuity, about atmospheric pressure, and volume flow rate. Learning these concepts might be very helpful for us in our life because, for example, you can use it if there's a leak in a pipe or something. You would be able to calculate the flow rate of the water leaking, and by knowing the area of the hole.
So, for my conclusion, I'm gonna say that the experiments were really interesting, and me that I took care of the calculating stuff. I found it like it was really easy to get because I understood the things we were seeing, and it was easy for me, and it was really fun to do it. And the experiments, I think they went really well, and we really learned something from that. And I think it was a good experience to do this because we learn how the pressure comes off and how with a bottle of water we can actually see how the the outflow and stuff like that. And I really like.
Hi, I am the theoretical research, and for this exercise experiments, I think that were really important. The knowing the volume flow rate, Bernoulli's theorem, and Torricelli theorem, because we use formulas of those theorems and with the principle of continuity and the atmospheric pressure, because with the experiments, for example, we use the volume flow rate to calculate the how do you say, the fluid, the ends of the fluid. And for example, in the Bernoulli equation, we know the flowing fluid in any point in the surface, in a surface. I mean, like, we use this equation for knowing the calculus of the water inside the bottle. In this point is like the surface, and we use the reservoir law. I mean, for knowing the speed of a liquid fluid under the force of gravity. We use this theorem in the part like we open the bottle and the water comes out is how do you say, more faster than the bottle close. So I think that the theorems and the principle of continuity and the atmospheric pressure, we use all of them for these experiments. So I think that it's really important to know the formulas and how the theorems works for doing this experiment. So